Hi, everyone, and welcome to another Quantitative Methods Network talk, or QMNET talk. My name is Mike Zephyr, and I'm an associate professor in the Faculty of Business and Economics at the University of Melbourne. And today we've got a really exciting speaker here to talk about a recent paper for the proceedings in the National Academy of Sciences. We've got Lawrence Saul talking about a tractable latent variable model for nonlinear dimensionality reduction. Let me say a few words about Professor Saul. You're a professor in the Department of Computer Science and Engineering at UCSD. It's such a beautiful campus. And your main research interests are machine learning and high-dimensional data analysis. You were previously the editor-in-chief of the Journal of Machine Learning Research, and you have a BS in physics from Harvard, the Harvard of the North, and a PhD in physics from MIT. And thank you so much for being here. We really appreciate it. I know it's kind of late for you, so thank you so much, and feel free to take it away.
Oh, you're quite welcome, and thank you for inviting me. It's great to speak to the other side of the world. Maybe one of the benefits of all this Zoom technology. So I'm going to talk to you today about a problem that I've been thinking about on and off for 20 years or so. But the good thing about this problem is it can be very easily described in less than 3 minutes. And it's really the problem of how to find low-dimensional structure and high-dimensional data. And for this talk, I'll be focusing on a particular type of low-dimensional structure that's fairly easy to visualize. One of the reasons I like this problem is it just combines elements of so many fields: statistics, geometry, computation. And the way this talk will work, first of all, keep it very informal, so feel free to interrupt with questions at any time or type in the chat box. I'll try to monitor that. I'm going to describe the problem and kind of what brought me to the point of this work. And then most of the talk will be describing a new model that I've just developed and I'm fairly excited about. And then at the end, we'll go over some results and discuss where there are many interesting future areas to do work in. And this is based on a paper that just came out. So if you're more interested in the details, go see the paper. But hopefully this talk is actually better than the paper because it can omit some of the details that aren't necessary for the central intuitions. So the basic problem is that high-dimensional data arises everywhere in science and engineering, whether you are working with collections of images or large collections of text or data sets from bioinformatics. And we would like to discover low-dimensional representations of those high-dimensional data sets. Those representations can have many uses. If you can represent high-dimensional data in 2 or 3 dimensions, then you can use the human eye as an aid to visualize the different modes of variability in the data, whether the data is clustered or it has continuous degrees of freedom. If you have a very large data collection and you have a low-dimensional representation, you can use that representation as something like an indexing scheme, right? If you want to find the nearest neighbors are much easier to find in low dimensions than in high dimensions. And then just in general, low-dimensional representations can reveal hidden structure in complex data. Just the fact that you can faithfully represent high-dimensional data in low dimensions tells you that there is some structure in your data set. So here's the problem statement, and I'll get back to those 2 images at the top in just a second. But intuitively, the idea is very simple. We have a large data set of high-dimensional data. We can think of every point in the data set as some point in a high-dimensional vector space. And somehow we want to unfold, compress, or project the data into a space of much lower dimensionality. And we want to do it in such a way that we don't lose information. So in particular, if you think about, I can only visualize this going from 3 dimensions to 2 dimensions, but think about points sampled in 3 dimensions on this kind of spiral-looking ribbon, right? And nearby points on this ribbon are kind of color-coded, so they have the same color. And we know that if we unroll this ribbon in 2 dimensions, we can represent the data faithfully that way, in the sense that nearby points stay nearby and faraway points stay far away. So that's the kind of unraveling or nonlinear projection that we're looking for. And to state this a little more mathematically, although we still have a ways to go to make it more precise after this, we're going to assume that our initial data set consists of what I'll call inputs high dimensional inputs in some big D dimensional space, call them x sub I, and there's little n of these. And our goal is to basically, for each of these inputs, to output an output, right, mu sub I, which is in this little d dimensional space, and we have one for every one of these inputs, such that hopefully this low dimensional space is much lower in dimensionality than the high dimensional space, and that only nearby inputs are mapped to nearby outputs, right? So I have to say what nearby means in this case, but hopefully this picture makes intuitively clear what I'm trying to do here. Okay. All right, so now I'm going to do a really brief survey of methods, and there's a huge literature on this, and there's going to be huge holes in my survey, but just enough to get us to the point where we can talk about something meaningful. So, the first types of methods you might explore are purely linear methods that just look for a linear projection of the data. And these are classical methods like principal component analysis, where you're basically taking high dimensional data and using eigenvector methods to compute subspaces of maximum variance. And these work really well, if you have two-dimensional data that lies on a line, you can project the data onto that line. If you have three-dimensional data or higher dimensional data that lies in a plane, you can project it down to that plane. But obviously, these linear methods cannot solve the problems that I've sort of hinted at in nonlinear dimensionality reduction. In particular, like if you wanted to unfold this ribbon, there is no linear projection that is going to map you down to two dimensions and keep nearby points on the ribbon nearby and faraway points on this ribbon far away. Okay. So we have to consider nonlinear methods. And 2 decades ago, about turn of the century, there was a kind of flurry of work in this area, and what I'll call spectral graph-based methods for this problem. I'm not going to go through all these methods individually, but the basic idea was to take the data set, construct some sort of graph that summarized which points were nearest neighbors of the other points in the data set, use that graph by some computation to construct a matrix, and then from the eigenvectors of that matrix, compute an embedding. And what was very appealing about these methods is that even though they were solving a very, highly nonlinear problems and not making any strong parametric assumptions, all these methods were rooted in very tractable and well understood optimizations. Things like finding all shortest paths through a graph, least squares reconstructions, computing eigenvectors of a graph Laplacian, or semi-definite programming. So even though the problem itself was very nonlinear, somehow all the nonlinearity was captured by the fact that knowing which points are nearest neighbors of the others, because nearest neighbors is kind of a highly nonlinear operation, right? Some points are in your nearest neighbor set and some points are out. So these received a lot of attention and they worked very well on many, many problems. But for problems in visualization, there has basically emerged a more popular class of methods that we'll get to next. Essentially, all these methods were making certain assumptions, and for data that didn't quite lie on a two-dimensional manifold or couldn't be really projected into 2 or 3 dimensions without losing some structure of the data, these methods weren't really the right fit. So by far, the most popular class of methods for these two-dimensional, three-dimensional visualizations are now kind of a family of what I call probabilistic methods for this problem. These are algorithms like t-SNE or largeviz or UMAP. And really the important thing of these algorithms is that they're all based on optimizing probabilistic notions of similarity, right? So they have some sort of a very flexible notion of which points are nearby and which points are far away. And there's some leeway in how you manage those relations. And these methods are different, but what they all share in common is that they all can be viewed as minimizing some sort of relative entropy or Kullback-Leibler divergence by gradient descent to compute an embedding of the inputs into some low-dimensional space. Okay? And these methods work very, very well in practice. They have produced some really remarkable visualizations of very large data sets. And with clever randomizations or efficient data structures and using GPUs and all sorts of tricks, you can get them to scale very, very well. Okay, and just as an example, here's sort of a canonical data set that people in machine learning often work with. It's a data set of handwritten digits. So every data point is really a 28 by 28 grayscale image of one of these digits, 0 through 9. And there's 70,000 images in this data set. And if you hand off this data set to these algorithms, you can ask it, produce a two-dimensional embedding of this data set where every image is mapped to a point in the plane. And when you give it to these algorithms, what you find, I've shown here the results for tsne and UMAP. Let's start with the ones for UMAP, because this one's easily color-coded, is that the different classes of images, even though you are mapping from a space which is almost 800 dimensional to a space with a two-dimensional, are nearly perfectly separated here. So these red dots correspond to, I think, images of zeros, and maybe these lighter red dots correspond to a different image class, right? And it's the clusters here are remarkably clean. And part of that is just because of the resolution of the image. There are some dots in here that don't show up on the screen if you blow it up. But the separation is just outstanding, and it's a highly nonlinear projection. And you see the same thing really in tsne. So over here, I haven't color-coded the embedding, but the color coding is shown in the bottom right corner. It really has a very almost ideal separation of these digit classes. And the algorithm has no knowledge of these digit classes or their boundaries beforehand. So given that success, I think you can ask, why am I giving a talk on yet another method for this problem? These methods are widely used in practice. They can also be used to validate the others, right? So they're different enough that they can act as sanity checks. What is left to explore? And what I hope to convince you of is that there's actually quite a bit left to explore, both conceptually and practically. So let me talk about sort of the questions that motivated this work. And the first question was, what sorts of optimizations should we expect for nonlinear dimensionality reduction? Now, first you might say, well, we're solving a very nonlinear problem, so we should expect a highly nonlinear optimization, maybe of the kind that deep neural networks are trying to figure out. And in that case, we really shouldn't expect too much from our objective function other than hopefully it's differentiable, right? And the objective functions for these popular methods, tsne, large viz, UMAP, they're differentiable. You can say that about them. You can do gradient descent. But that's really about all you can say about them. And you might hope that there are lurking in the background perhaps some more elegant or structured optimizations for this problem. Why might you hope for that? Well, first, there were all these spectral graph-based methods that didn't work as well as these three up here, but those were all based on much more structured types of optimizations. And the other thing that this problem has going for it is that essentially, if you're trying to construct a neighborhood embedding, you're dealing with a sparse graph that summarizes which points are neighbors of one another. And sparse graphs just are known to have a ton of structure, right? There's this whole area of spectral graph theory, which is dedicated to representing sparse graphs as matrices and then doing clever optimizations on those matrices. So that's one reason you might hope for some structure, even though we're solving a nonlinear problem of this form. The second question that animated me in this work was, what types of probabilistic models should we expect for nonlinear dimensionality reduction? And there are really a sort of a class of canonical probabilistic models known as latent variable models for finding other types of structure in data. So for clustering, there are Gaussian mixture models. For discovering subspaces, there's factor analysis, which is really just a probabilistic version of principal component analysis. There's things like Kalman filtering. And the thing is that though tsne, large viz, and UMAP are all dealing with probabilistic notions of similarity, and they're minimizing things that can be considered KL divergences or relative entropies, they don't look anything like these well-established latent variable models, right? There's no latent variables that you're integrating over. So why is that, or why isn't that? And it's natural to ask, is there some sort of tractable latent variable model for this problem? What I mean by tractable here is that there are latent variables that you don't observe, but in fact, all the averages that you would need to do to compute their expected values or their variances are tractable. You can do them analytically. somehow this problem seems to lend itself to a latent variable. Or if I state it this way, I'm given some high dimensional inputs. I want to infer a collection of outputs that are neighborhood preserving. That sounds a lot, I mean, except for that very last line, it almost sounds like a problem in clustering. Like I'd say, given some high dimensional inputs, infer a collection of prototypes that sort of represent uniformly sampled points in the data, right? Or for factor analysis, given a set of high dimensional inputs, infer a set of base vectors that could be viewed as basis vectors for a subspace that spans the data, right? So the criteria we're using at the end is different. We want a neighborhood preserving embedding, but it seems like these outputs should be parameters, could be parameters in a latent variable model. Okay, so what I'm going to try to do in this talk is to answer those questions. The first is to convince you that there is, in fact, a tractable latent variable model for nonlinear dimensionality reduction. And if you're familiar with things like Gaussian mixture models or factor analysis, I want to convince you that this problem joins that family of sort of canonical problems where there are these latent variable models where you can do all the integrals tractably, okay? Even though it's not going to be a purely Gaussian model. The second point I want to get across is that this sparse, oops, not the third point yet, the sparse graph at the heart of all these neighborhood preserving embeddings is going to give rise to some structure that we can exploit in the optimization and the fitting of this latent variable model. In particular, there's been a really long line of beautiful work in theoretical computer science for taking sparse graphs, constructing their graph Laplacians, and building extremely fast solvers for linear systems that are based on these graph Laplacians. And we're going to see that the model I propose can use these extremely fast solvers as a core primitive, right? So something a little bit more structured than just following the gradients. And the third thing I want to do, if there's time for it, is to convince you that there's sort of an interesting way to break what is often the main computational logjam in these models. When you're trying to construct a neighborhood preserving embedding, you have to do two things. You have to make sure that nearby inputs are mapped to nearby outputs, but you also have to make sure, and this is one of the things that the earlier methods didn't do as well as these probabilistic ones, you have to make sure that far away inputs also stay far apart from each other. And that means that, if you have n inputs and most of them need to stay apart from each other, you sort of generate order n squared interactions between the inputs that have to be respected to make distant points stay distant. And that's, that's polynomial, but when n is large, you can't deal with n squared. So we have to look for ways of managing that logjam as well. All right, that is the basic introduction. And I should add, in addition to answering these questions, we're going to come up with a fairly effective algorithm, right? So when we apply it, for example, this data set of digits, it also is going to separate these digits in a fairly nice way, even though it has no knowledge of the digit class labels beforehand. So before I dive into the model itself, this would be a good time to take questions, about the problem or the history or anything that's not clear. Anything yet? Like there's a saying, silence implies consent, but that's often not the case in academic talks. So feel free to ask questions. Okay. If not, let's keep going. Right. So now we're going to get to the model itself. And like I said, I'm really going to steer away from technical details and just try to give what I hope are the main ideas of this model. Okay, so here's the idea in a nutshell. We're going to have a probabilistic model, and this model is going to give us basically a mapping from the inputs into a latent space of lower dimensionality. If the inputs, I use X to denote them, I'm going to use H to denote kind of the coordinates in this latent space, because I think of these things as hidden variables. And I'm imagining what I'm trying to learn here is some distribution that, given input, maps it stochastically into this space. Now, this is a probabilistic model, so it's going to have some parameters. And the idea is, very simply, we're going to adjust the parameters of this mapping So that with high probability, the mapping satisfies our criteria for a neighborhood preserving embedding, right? Which is that only nearby points in the input space are mapped to nearby points in the output space. And I say with high probability because remember, this is in general stochastic mapping. All right, so what's the key thing the model has to do? Well, it has to achieve this balancing act. Basically, the likelihood that we only map nearby inputs to nearby outputs means we have to keep nearby inputs together while keeping faraway inputs apart. And you can see that these two goals are in conflict because one easy way to map all nearby inputs together is just to map everything to a single point, right? That keeps all the nearby inputs together. But unfortunately, it keeps all the inputs together, right? And one easy way to map all the distant inputs apart would just to send everything to infinity, but then the nearby inputs would be together. So somehow we've got to balance these two goals in just the right way to get a neighborhood preserving embedding. All right, so here is what we need to do. Here are the kind of the steps I'll go through in varying levels of detail depending on where you guys stop me with questions. So first, how to define this model, how to estimate the model, and then how to scale it to large data sets, right? Not just data sets with 100 or 1,000 points, but 10,000, 100,000, right? Data sets where it's too large to construct sort of an n by n matrix explicitly. All right, so first, how to define this model. It's a pretty simple model to define. So this part's not too hard. Here's how we're going to parameterize the model. For every one of these high dimensional inputs, we are going to associate two parameters. First parameter we've already seen. It's the low dimensional output. This mu sub I is now a parameter of our latent variable model. It lives in this d-dimensional space. And there's going to be one other parameter that I'm associating with each high dimensional input, which is just a variance parameter. And it's going to describe, roughly speaking, the uncertainty of when I try to map my high dimensional input into the latent space. And here's how I'm going to embed the inputs once I have these parameters in a very simple way, right? I want a mapping from the inputs to the outputs stochastically. Essentially, I'm going to treat this output as the mean of a multivariate Gaussian with a diagonal covariance matrix. So this is just a little d-dimensional multivariate Gaussian in the latent space with mean mu sub I. And this is how I'm going to, since I have one of these parameters and one of these variances for input, this gives me now a probabilistic mapping into this low dimensional space. Okay. All right. Well, like I said, our goal is to keep nearby inputs nearby and keep faraway inputs far away. To make some progress on that, I have to tell you what it means for two inputs to be nearby, right? I have to come up with some definition of nearness, or sort of how do points meet their neighbors in the original data set. And I'm not going to spend too much time on this, but this is actually really important. In fact, I had all the estimation equations for this algorithm worked out. I had a beautiful framework for scaling it. And for 2 weeks, I didn't construct this graph in a careful way, and I was going crazy about why the model wasn't working. So, I mean, the basic idea is pretty simple, right? We're going to encode the neighbors by a sparse graph. So hopefully you can see here, this is sort of a graph that's a skeleton of this data set where I've drawn edges between nearby points. And I'll call this sparse graph F. Both it's a similarity graph and it's sparse, so S makes sense here. I and J will be an edge in this graph. They connect the points Xi and Xj. We can also regard this graph as a sparse, n by n binary matrix, which is 1 if there's an edge from I to J. So how do we construct this graph? Well, the simplest way to do it, and this is what your intuition should basically be, is that we choose some parameter k, and we'll say that the edge ij is in this graph if xi is a k nearest neighbor of xj, or vice versa. Right? That's the simplest way to construct the graph, and that's the basic idea. And for a lot of data sets, that would actually work. But when you have outliers, this simplest type of graph, which is this is a symmetric undirected graph, right? It doesn't necessarily handle outliers too well. At least that was my experience. And so one way you can make this graph slightly more robust, one very simple way, is just to require that you only have an edge if xi and xj are mutual k nearest neighbors, right? So that if something is an outlier, that will tend to reduce its connectivity to other points in the graph. Okay, well, we can't, in practice, I found you can't quite just stop there, because reasonable values of k that you might want to use to create this mutually k nearest neighbor graph are such that the graph as a whole is not connected. And we really do want the graph to be connected if we want to visualize the data set all at once. And so the last thing we do, we take a simple graph, we make it more robust, but now we just add in a few more edges to make sure it's connected. And the way we do that is we just take our original graph, construct the minimum weighted spanning tree. So the sort of the minimum tree of inputs from this original graph that make it connected, and then we add those edges in, okay? So it's essentially something like the k nearest neighbor graph, but a little bit more robust with just enough edges to make sure it's connected. Okay? And none of these ideas for making a graph robust or connected came from me, but they were actually investigated for these earlier spectral graph-based models of nonlinear dimensionality reduction. All right, now we have a notion of which inputs are nearby. How are we going to test that our model is working well, right? So what I want you to do is just consider a pair of inputs that I've told you are similar. Okay, so there's some edge in the similarity graph that connects them, and now they are stochastically mapped to the latent space, which means that I do this little experiment. I take the ith input and I sample some vector h in my latent space from a Gaussian with mean mu sub I and variance is sigma I squared in every one of its coordinates. And I do the same thing for the input x sub j. I sample an output centered at mu sub j with this variance, and I'll call it h prime. Okay, so the ith input gets mapped to h, the jth input gets mapped to h prime. And what do I want? If I want these inputs to be nearby, the criteria I'm going to use is basically that with high probability, the distances shrink, right? Because if the distances shrink between nearby inputs, then in some sense they aren't getting any further apart than they already were, right? So how am I going to measure that? Well, I'm going to construct a binary random variable. I'll call it C plus because I want this variable to be 1. It's kind of a detecting coincidence in the latent space. And the idea is this variable will be 1 with high probability if the distance between h and h prime is less than the distance between the inputs xi and xj. And don't get too confused here. I put this in a factor of 2 as a base, which just means if the distance between h minus h prime is very small, this is 1. The distance between h minus h prime is very, very large, this goes to 0. And these distances are exactly the same, then this probability is exactly 1/2. So I've just sort of chosen this base 2 here to calibrate the probability. So 1/2 means I haven't done anything to the distances. I've kind of preserved them. But in generally, I want to shrink them. Okay, well, now with this variable, I can ask a meaningful question. Are the inputs xi and xj faithfully embedded into the latent space? And to do this, I will measure the success of this experiment by computing the probability averaged over all possible places where I map them to, given that I map them to these means with these variances, that this coincidence detector basically fired, right? And so the way I do that is I map the points with these Gaussians to the latent space. I compute the probability that there's a coincidence, and then I average over all the points in my latent space. This is the sort of key idea here, that this probability measures how well these inputs are mapped close together. Are there any questions about that? You guys are a great audience in the sense that there's no hecklers. Okay, so what else do we want to do? We don't just want to keep similar inputs nearby. We want to keep dissimilar inputs apart. Okay, so dissimilar inputs are any inputs that aren't connected by my similarity graph. Okay, so now imagine a different experiment where I take 2 inputs in my original space. Think about them, they're being far away. Again, they are stochastically mapped to the latent space by this probabilistic mapping that depends on these parameters that I want to adjust. And I get these new vectors in my latent space, h and h prime. And now with high probability, I want these things to be far apart. Okay, so how do I enforce that? Well, think about it like this. If I'm taking the ith input and I'm mapping all of its nearby points to something closer than they were before, to make sure that this new input xj that I want to be far away from xi doesn't invade that neighborhood in my latent space. Basically, I want to keep xj further apart than any distance from x sub I to one of its neighbors. And that's what this thing on the right is saying, right? The max over k of all the distances to similar inputs of x sub I, because Si of k is only non-zero, is only equal to 1 for neighbors of x sub I, okay? And I want to do something similar in the reverse direction, but we'll just handle that with a double sum, okay? So if I have this, it means that the jth input in my latent space is never going to invade the neighborhood of neighbors of x sub I if those neighbors I've faithfully mapped as well, okay? So if you understood that, then what goes next is just the same. I'm going to create another binary random variable that detects coincidences. These are going to be coincidences of pairs of dissimilar inputs. And I'll calibrate so this probability is exactly equal to 1/2 if these distances are the same. But now I want this distance to be very large. And if this distance is very large, then this probability will be very small, right? Which is, in fact, what I want. How can we measure the success of this experiment? Are these inputs that we want to be far away faithfully embedded? Well, now, instead of computing the probability this is 1, we are going to compute the marginal probability that they don't coincide. Okay, so we map them via these Gaussians into the latent space, and then we average over the opposite of this probability, which is just 1 minus this term here. All right, that's all there is to the definition of the model, right? What do we want to do? Well, we want to keep all the nearby inputs nearby, all the faraway inputs far away. And we can do that by constructing an objective function that basically sums over all pairs of inputs. For all the pairs of inputs that should be similar, let's try to maximize the log probability that they coincide in this stochastic mapping. And for all the pairs of inputs that are dissimilar, so this S bar ij is just the complement of the similarity graph. It's 1 for all things that aren't connected by the similarity graph, right? For all these pairs of dissimilar inputs, maximize the log probability that they are not mapped close together. And I'm going to normalize these different terms so by the number of edges in this graph. This graph is very sparse. This graph is very dense, which is why we'd like to normalize by the number of edges. Okay. So hopefully that strikes you as a reasonable objective function. Certainly, if we could get all these probabilities to be very large, we should have a neighborhood preserving embedding. Okay. So there's 2 ways to interpret L. One is the one I just gave you, right? It's an objective function for the parameters of this stochastic neighborhood preserving embedding. The other way to interpret it is the normalized log likelihood of a latent variable model, right? I mean, these are just log marginal probabilities. The way we're computing these marginal probabilities is by integrating over latent variables that have these Gaussian priors. So we can think about this as a log likelihood. And if it's a latent variable model, we can ask, can we use the machinery of maximum likelihood estimation for latent variable models to estimate its parameters? And then the first question you have to ask is the model tractable? I've sort of been a little bit cavalier here about writing down these integrals, right? These are not one-dimensional integrals or two-dimensional integrals that you can necessarily do by like simple quadrature if you had to. H and H prime are each little d dimensional variables, but little d could be 2 or 3, or it could be 10 if big D is 5,000. So can you do these integrals? And right, here's the question: is the model tractable? And as the saying goes, there's kind of good news and then there's bad news. Now, in fact, in this case, I would say that the good news does outweigh the bad news, but it's not as simple as some of the other latent variable models like Gaussian mixture models or factor analysis that you might be familiar with. But the good news is that the model is, in the end, tractable. So let me explain that. Why do I say there's some bad news? And why I say there's some bad news is that this model is not like a jointly Gaussian model, and that's because some of the variables in the model are binary, right? There are these coincidence detector variables that are binary random variables. And so when you want to compute, say, the posterior distribution over these latent variables, H and H prime, given, say, I'm mapping 2 endpoints and I know they're not supposed to coincide. Given that they shouldn't coincide, what's the posterior distribution over H and H prime? Well, how do we compute posterior distributions, right? We use Bayes' rule, so we write down their priors and how they're related. And you don't even have to go very far in the math just to see that this thing is not going to be Gaussian, because the two prefactors are Gaussian, but for this, this probability that they don't coincide, it was 1 minus some exponential, right? Here I've converted it to the base e from base 2. You can always do that by choosing this parameter delta carefully, right? So this overall thing is not multivariate Gaussian. And normally that's like the death knell for a latent variable model in terms of can you do it tractably. But even though that doesn't typically bode well, in this case, we just kind of luck out. And why do we luck out? Because in this case, this posterior has a special property, right? This thing is not multivariate Gaussian, but you can see right away that the first term looks like a Gaussian, and this, if you were to multiply all these out in the second term, it looks like a Gaussian. And so in fact, this posterior distribution, you can express it as the weighted difference of two multivariate Gaussian distributions. So all the integrals that we need to do, they're not Gaussian, but you can do them, you can get them from the difference of Gaussian distributions, right? So that's just kind of a lucky circumstance that we're going to exploit. And what I mean by that is all of the following can be computed analytically, right? So for pairs of similar inputs, we can compute the likelihood that they're mapped to nearby points in the latent space. We can compute the posterior means of these latent variables, h and h prime. We can compute the posterior squares. And we can do all these things for pairs of dissimilar inputs as well, right? And these are the distributions. These posteriors are actually multivariate Gaussian. These are the ones that aren't, but they're still tractable. Okay. The paper has all the calculations. All you really need to know is that you can do them. All right. So that's how you define the model. And hopefully I've assured you that the model is in fact tractable. And now the next question is how to estimate the model. But again, this is a good place to stop and ask, are there any questions about what I've done so far? Or maybe confusions?
I think people might be waiting until the end. I mean, writing down questions, and then there may be a
too. But I
barrage or
encourage them
onslaught.
to write them in the chat as well, because if something is unclear, there's probably other people have the same question. Or if I'm just, it's hard to know if you're going too fast, right? So feel free to slow me down in any way. You can even like ask about the weather if necessary. Right, okay, so the next question is how do we estimate this model? And again, I'm trying not to do too much in the way of details, but it's a probabilistic model. It's a latent variable model, has parameters. We're gonna try to maximize our objective function, which was a weighted log likelihood. So we'll use maximum likelihood estimation. And I want to appeal, hopefully, to some familiarity you have with these other canonical latent variable models, right? So if you're familiar with things like factor analysis or hidden Markov models or Gaussian mixture models, right? How are these models estimated? And there's kind of a classic approach for all these models. There's something called the expectation maximization algorithm, and it's a kind of iterative two-step algorithm. And it's called the EM algorithm for short, because in the E step of this algorithm, you essentially compute a bunch of statistics of the posterior distribution over your latent variables. And in the M step of these algorithms, you use these statistics to update the model parameters, right? And this basic framework can be applied really to any latent variable model in which you can compute these averages, and in which the M step turns out to be sort of a tractable optimization. When the latent variables have Gaussian priors, though, the M step is really fairly simple. And so it's just a question, can you compute these posterior statistics, okay? So this is a well-known alternating iterative procedure for latent variable models. And the nice thing about it is that it converges monotonically in the likelihood, right? So every step of this procedure, is improving your model by the objective function that you're using to measure how good it is. Okay. All right. So how do we implement this model in our case? Again, it's just a high-level sketch. Basically, we have to compute a bunch of posterior statistics. And you don't really have to remember what this notation is. You just have to know that phi ij and phi prime ij are computing something like posterior variances for pairs of inputs that I've called similar, right? Given that these inputs are supposed to coincide in the latent space, right? And there's a bunch of other posterior statistics that you have to compute for every pair of dissimilar inputs, which are the posterior means that these variables h and h prime get mapped to, and also some measure of their posterior variance, their sort of difference from where we expect them to get mapped to, right? So these are a whole bunch of things that you have to compute, and all you need to know, right, is that these statistics can be computed analytically. And when you see things on the next slide, is the only place you'll see them. When you see things like phi and psi and h bar, just think of them, they're just statistics, they're just numbers that we know how to compute. Now, I am fudging one thing here, right, which is how many of these statistics are there to compute, right? For pairs of similar inputs, well, this is a sparse graph. So there's really, if we have n inputs and every input is similar to, k, where k is some small number, then there'll be roughly order n of these guys to compute in this step. But for pairs of dissimilar inputs, right, there are order n squared pairs of dissimilar inputs. So these are a lot of statistics to have to compute. And I don't want my algorithm to scale like order n squared. So for now, let's just accept the fact that all these statistics can be computed analytically, but I'm going to have to come back to a sort of more clever way to deal with this problem later. Okay? Given that you have these statistics, right, what is the M step for this model, which is to say, how do you re-estimate the parameters? And what are the parameters again? There's one low-dimensional output, mu sub I, that corresponds to every input x sub I, and one scalar variance sigma I, or sigma I squared, that also corresponds to every input. Okay? So suffice it to say that the updates take a very simple form in terms of these statistics. So as shorthand, let little s and little s bar just be like the normalized similarity and dissimilarity matrices. And again, the specific form of these isn't too important. The only thing that matters is that, they fit on one slide, right? They're simple. They're simple to code up. So there's some very simple formula in terms of all these posterior variances and the edges in the similarity graph and the edges in the dissimilarity graph for how you update the individual variances. And for updating the outputs, which are really the key parameters of the model, right? Because they tell you where every input gets mapped to. For updating the outputs, you have to solve some linear system, some n by n linear system, okay? So A here is some n by n matrix. And remember, these posterior means are vectors. So this whole thing is a vector, we multiply it by a matrix, right? Solve this linear system. And the nice thing about this linear system, the only thing you really need to know is that this linear system, this matrix A is symmetric diagonally dominant, okay? So in fact, it's a very sparse matrix. It has the same sparsity pattern as a similarity graph. And if you add up all the off-diagonal elements in, say, every row or column, they are sort of sufficiently small compared to that diagonal element in this matrix. And that's going to be very useful, right? Because in general, to solve a linear set of equations, that's n by n, it's order n squared, right? And I've already told you, we don't want to scale like order n squared. All right, so what are some nice properties of these update rules? The first one I've already mentioned, it's just guaranteed. If you can derive an expectation maximization algorithm and implement it, you're guaranteed that these updates are going to improve the model's log likelihood at every step, right? So here's the model's log likelihood. It's just a sum over similar pairs and dissimilar pairs. For similar pairs, the log probability that these similar inputs coincide. For dissimilar pair, the log probability they don't coincide. And we don't, one problem with gradient descent is that you just have to deal with these pesky learning rates. For some people, they don't care. They're used to it and they're enamored of it. I've got to admit, I never got used to gradient descent, and learning rates, they're always my downfall, having to choose them in a large problem. So I like this feature. I won't claim that it's inherently better. It's just sort of maybe your personal preference. But here's one thing that actually is quite nice. And that's what I referred to earlier, which is that there are extremely efficient solvers for these symmetric diagonally dominant linear systems. And why it's nice is that there is something called the Laplacian paradigm in theoretical computer science, which is this basic idea that whenever you have a problem involving a sparse graph, you should try to reduce that problem to something where the core primitive is solving a linear system of this form that arises from the discrete graph Laplacian, right? And this paradigm has been carried out for all sorts of problems in like social network analysis, different types of graph embedding, you know, diffusion models, you know, tracing the spread of epidemics, all sorts of things. But it hasn't really been applied, hasn't really been realized for this problem of nonlinear dimensionality reduction, despite the fact that there is this sparse graph lying around in the background. Okay, so it's quite a nice thing that the estimation step for the outputs, which are really the key parameters of this latent variable model, are re-estimated by solving a SDD, sparse diagonally dominant linear system that arises essentially from a discrete graph Laplacian of the similarity graph. Okay, this is another good point for questions. So now, you know, the next thing to talk about is something I punted on earlier, which is how do you scale this model, right? In particular, just to compute this objective function, forget about estimating the parameters, just to compute this objective function looks like it involves a sum over order n squared pairs of dissimilar inputs. That's already kind of a showstopper if you have 100,000 inputs. But any questions about what I've said so far? So far, so good. All right. So how do we scale the model? Okay. So again, this original log likelihood, look, like I just said, it has this worrisome term that I put in red here. How are we going to manage these orderly n squared pairs? And I should say that the objective functions that are maximized by UMAP and large viz, these two other probabilistic methods that I referenced earlier that are extremely successful, have a very similar form as this. They also look like a sum over pairs. They look like a sum over log probabilities. Now, these log probabilities aren't derived from a latent variable model, which is why they go down the route of gradient descent for optimizing their model. But they encounter exactly this problem, where they have order n squared terms. And then what they do is basically they use a random sampling of these pairs. Okay? And again, that is one approach that you could use. It's not the approach I followed, because I thought there was something else that I wanted to explore. But that is the approach they use. Just take some random sampling. The problem with the random sampling, it sort of introduces another parameter in the problem, which is how dense is this random sampling, right? And the results can kind of depend on that. So what I'm going to do is borrow a concept that's sort of very familiar in many different areas of applied mathematics and statistical physics, which is to take a model, sort of a n-body problem that involves order n squared pairwise interactions, and sort of to reduce it to a simpler model that involves many fewer pairwise interactions, but that at what they call a coarse-grained level, right? It's sort of if you look at it with your eyes squinting, everything kind of looks the same, right? And the idea to this is we're going to construct a recursive approximation to this log likelihood, where we can trade off accuracy on extremely short length scales for speed. Okay? So at a very high level, how this approximation is going to work is going to be recursive, and at the 0th level, I'm not doing any approximation, and that's just optimizing this original likelihood, and it will scale like order n squared. And what I'm going to try to convince you of is that if we do one level of this recursion, then if we're sort of lucky on how we do it, this isn't a rigorous theoretical analysis. It's sort of a suggestive theoretical analysis that it would scale as order n to the 4/3 instead, right? Which is, of course, much better. And although this isn't a rigorous analysis, I should just say empirically in practice, you do see a huge gain, right? And you can repeat this recursion, and every time you repeat this recursion, you kind of get this power to be lower and lower and get closer and closer to linear, right? And again, these aren't rigorous, but you'll understand how I get these sort of modified exponents, and that would sort of hopefully it will give you some faith that empirically the speedups I'm talking about are in fact realized. Okay, so what is this recursive approximation? And again, you don't need to understand the details to understand how it works, and that's why I think the talk actually has an advantage over the paper, because in the paper you're bound to you have to explain anything in the amount of space you're given. Right, so here's the idea, right? Before coarse graining, let's say we're trying to compress or embed this high dimensional state of digit images, right? So every digit image is a point, and some images are nearby to others, but others are very far apart. So like all these 4s and 9 are very apart from these 3s and 8s, and these apart from these 2s. And so if I want to think about the dissimilarity graph, right? The graph that connects dissimilar inputs, it's incredibly dense. Every one of these red lines connects some pair of dissimilar inputs, and every one of these red lines contributes a term to the log likelihood, okay? And there's order n squared of them. Okay, so that's what the model looks like before coarse graining. Here's how coarse graining works. It works in a number of steps. And the first step is to basically sample just some of these points in your data set randomly and to call them landmarks, okay? So for example, maybe I've put these landmarks in green here. So maybe this image of a 2 is a landmark. This image is a 4 is a landmark. This image of a 3 is what I'm calling a landmark. So I'm just choosing some number of points randomly from the data set, right? So let's call this number of points n sub L for the number of landmarks. I've shown 3 here, but in general, this is not going to be a small number. It's going to be large enough to sort of get a pretty good cover of the data set. And we're going to talk explicitly later about how many I have to choose, okay? So the first step is just to choose these landmarks, choose them randomly. Okay? Here's the second step, okay? This is going to seem like a huge step. Don't worry, we're going to correct for it later. Delete all the dissimilarity edges between non-landmarks, okay? So don't require the log likelihood to keep any pairs of inputs far apart, except explicitly for the inputs that are designated as landmarks. Okay, so I'll keep this 2 far from this 4 and this far from this 3, but I've dropped all the other terms. So that's great. Now I've sort of sparsified the model, but obviously this isn't going to work if I leave it at that, because I need to sort of keep this whole bunch far away from this whole bunch, and et cetera. So what's the next thing I'm going to do? Again, this is just sort of thematically here. The next thing I'm going to do is what I call anchoring. I'm going to add some new terms to my objective function. What I'm going to do is every one of my points in my data set is going to be closest to some particular landmark, right? I can just, it's like a k-means algorithm. I can assign it to that landmark. And now I'm going to add a new similarity edge from every input to its closest landmark. Okay, so I'm going to enforce on some length scale that these inputs actually can't get too far away from their landmarks. Okay. Now what I'm going to do is I don't want to go backwards. I'm going to take these edges between the landmarks and upweight them. Okay. In particular, if there were 5 images here, or 5 points that sort of were grouped with this landmark, and 5 points that were grouped with this landmark, I'm going to upweight this edge by a factor of 25, 5 times 5 here, right? So it's kind of like this edge is now carrying all the weight of all the edges that went before it, right? Same for this edge, same for this edge, okay? So what have I done? I've said, okay, it's really important that I keep these landmarks far apart. And at the same time, it's now actually kind of important on some length scale that these points don't get too far apart from the landmark from which they're anchored. Okay? Now here's where I'm going to elide some of the details in the paper. Okay? But you can trust me, if you do this in a careful way, by the triangle inequality, you're going to essentially preserve all the repulsive interactions of the first case, right? Because if I keep these 2's fairly close to this one, and I make sure that this 2 is very far apart from this 4 and then this 3, then by the triangle inequality, all these 2's are also going to have to be very far apart from these 3's and 8's, and very far apart from these 4's and 9's and this 4's. Okay, so in fact, I don't just have to upweight these edges, but I have to slightly adjust the length scale that I repel them at. Okay, but that's the very basic idea behind coarse graining. Again, are there any questions on that idea? Hopefully, it's fairly intuitive, right? Sparsify, use the triangle inequality, upweight so that the sort of order of magnitude of all the original interactions is preserved. Okay, fantastic. You're giving me a false sense of confidence here, but I'm gonna keep going. How many landmarks to choose, right? So clearly, if there's sort of a trade-off here. If I choose if I choose the same number of landmarks as I have inputs, I haven't gained anything. Somehow, if I choose too few landmarks, right, then in fact, the number of similarity edges that I have to add inside of each of these boxes is going to be very large as well, right? So how many landmarks to choose? So we're going to do a sort of very simple idealized experiment. Are the landmarks random or chosen to be the furthest apart? Excellent question. So that's a great intuition that you'd want to choose the landmarks to be sort of furthest apart. And the first thing I tried was some sort of greedy algorithms based on like choosing centers greedily farthest to be apart, of which there are some guarantees that things are not off by more than a factor of 2 from the optimum. And what I found was that choosing them randomly worked better. Okay, so there's so in fact they are chosen randomly, and I don't know if that's just because the greedy algorithms that they have some optimal guarantees, but on average the random one works better. But yeah, I just chose them randomly, and that seemed to work well. But that is a random step in the algorithm, right? So how many of these things do we have to choose? So let's assume that we get very lucky, okay, and the landmarks are evenly distributed among n inputs, okay? So what I mean by that is that for every landmark, there's n divided by n sub l inputs that are sort of anchored to it. So in that case, how many pairs of dissimilar inputs remain in the log likelihood? Okay, so we have these graphs and we have these terms, or I have to say, how many pairs of terms remain in the likelihood if we do this? Okay, so before coarse graining, there are order n squared over here. What happens after coarse graining? Well, now we have order nl squared, right, from all the landmarks that are interacting pairwise with one another. But one thing we also still have is, right, we have all these terms, these sort of additional similarity weights that we have to add, and other weights that we have to add sort of inside these boxes, right? Okay, and there's n sub l of these boxes, and there's this many points inside the boxes, and so you can just sort of do a simple optimization here. How many of these? How should we choose n sub l to sort of minimize this expression? And if you choose n sub l to be n to the 2/3, this overall expression gets reduced to order n to the 4/3. Okay, so in this idealized case where the landmarks are sort of evenly distributed, this is a nice reduction. Okay. Now, okay, so you don't expect to realize this in practice, but you might hope to get something, something similar. Now, what if this is still too large, right? So one of the data sets I applied it to was, 200,000, and n to the 4/3 is still pretty big. Well, then you just kind of recursively apply this idea, right? So you have NL landmarks. Now you subsample n to the L 2/3 of those landmarks, and you call those super landmarks, and you model their separation at even longer length scales, right? And then within each of the boxes that each landmarks, you sort of subsample those inputs as sub landmarks, and you model their separation at shorter length scales, right? And you just sort of keep on recursing until you get down to something that's more manageable, right? And again, I'll just say that in practice, on the data set, the larger one that I experimented on, it had about 200,000 inputs, and I was trying to construct a 10-dimensional embedding. Each iteration of EM on the laptop, this 6-year-old MacBook Air that I'm giving the talk on right now, took less than 4 seconds. Okay, so and it would have been totally impractical without this recursion. So at least although these theoretical they're not guarantees, but in practice it really does seem to improve the scaling of the algorithm. Okay, and like I said, you can do this more and more. All right. All right. Okay, so now we actually get to the results. And any questions? Okay, we started a bit late. I actually think we'll finish on time. So here's the first canonical data set, and I'll show a couple of results on this data set because it's actually quite interesting. There are 70,000 of these images. just to make the nearest neighbor calculations more efficient, I use PCA to map them down to 50 dimensions. But ultimately, I'm going to be trying to map them down to 2 dimensions. So I still have a lot of work to do by nonlinear embedding. And for this particular results, I used 1 round of this coarse graining procedure, right? Because without 1 round of this coarse graining procedure, I couldn't run the algorithm. 70,000 is too large. I don't want to work with 70,000 by 70,000 matrices. Here's what the model does with these inputs. And I've just shown a heat map here. So I haven't shown you what any of the, where any of the image classes are mapped to. I've just sort of done a logarithmic heat map here. So the brighter the pixel that you see in this thing sort of corresponds to, like twice as many points were mapped to that space, right? And hopefully you can see with this heat map that there are sort of fairly well-defined clusters, right? And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, if you kind of know what you're looking for, right? And really, if you zoom in, you can see the separation in these things a little bit better. But I can't show that on this screen here. Okay, let me show you what the colors look like, okay? Because this gets even more interesting. So here are the colors. You can see there's some spatter in between, and I'll get to that in a second. But what's really kind of interesting is that the digits that you might think are more confusable are actually the ones that are closer in this embedding. So right, these pairs of sort of dark green are the 5s, right? And these yellows are the 3s, and these over here are the 8s, right? And you can kind of see that these images on the top are fairly clean, but if you start getting messy versions where the images of the 5, you just need 2 edges here to turn it into an 8. And you delete these 2 things on an 8, you can get a 3, right? So 3 5s and 8s are grouped together. 4 7s and 9s are grouped together. Again, if you put a bar across this 4, it easily becomes a 9. And sometimes you have 4s that are written more like this, with a slanted top, in which case they can look quite similar to 9s. And if this oval gets squished, this 9 can turn into a 7, right? And that's precisely why these things get mapped together. And then these other digits that just don't really look like other digits at all, like 0s and 1s, they're sort of very well localized in this 2-dimensional space. Okay, so what I've shown here are the outputs, right? The mu sub i's, the low-dimensional, two-dimensional output that corresponds to every input. But there are also these parameters in the model that are the sigma squares, right? So for every input, we're also estimating a variance. And this variance basically tells you how confident I am in localizing that input to a particular point in the latent space to preserve all these things. And so another thing you can do is just, well, let's ignore the inputs that we're sort of least confident of, right? So let's take the 5% of inputs for which these estimated variances are largest, right? And are those outliers? Well, if we just delete those from the plot, and that's what I've done here. I've kind of shown this subplot shows a histogram of these variances. And if I cut out the top 5%, which have the largest values, and this is a logarithmic scale, the scatter plot goes from something like this, which has a lot of gook in it, to something that's even much cleaner, right? And now you can ask, are these things, do they really correspond to outliers? If I were to look at the things that have these high variances, do they correspond to digits that might be hardest to classify? And so these are kind of the digits that correspond to the points that are circled here that have the highest variance. And maybe hopefully they show up a little bigger on your screen than my tiny laptop screen. But if you were to zoom in here, a lot of these things do not look very typical for the classes they represent, right? You have sort of weird looking 9s and scrunched looking 6s. Is that a 5 or a 6, right? Is that a 2 or a 7, right? Sometimes they're very thick. And so I wouldn't say it does a perfect job of catching outliers because some of these things are outliers, but they're highly recognizable. But certainly they're outliers. They don't look like most of the zeros. Okay. Let me mention one other result just to get away from 2-dimensional embeddings, because one of the nice things about this model is that you don't have to embed into 2 dimensions. You can embed into larger numbers of dimensions. So as a fun experiment, I tried one other data set, which is a data set of roughly 207,000 vectors that were each 3-dimensional. And these vectors were estimated by a very complex neural network. It's called a word-to-vec model that was trained on the Google News corpus, right? The huge corpus of text. And the output of this training procedure was a 300-dimensional vector for essentially every word in the English language. And I took a subset of the sort of 207,000 words that are in the WordNet database, so they sort of correspond to real words as opposed to sort of garbage words that occur if you look at a large enough corpus of text, and just try to embed those 300-dimensional vectors in a smaller space to just see what could be done, right? So after 400 iterations of EM, and in this case, the data set was large enough that I needed to use 2 of these rounds of coarse graining to get these results, I produced a 10-dimensional embedding. Okay, so this is a 30x reduction in the dimensionality. And what was interesting here is that nearly 40% of words, when you map from 300 dimensions to 10, actually retain the same first nearest neighbor, right? So that's kind of it's a fairly good recall. You know, your first nearest neighbor for almost half the words stayed exactly the same. And if you were to compare that to, say, a linear embedding to get that same degree of recall for that first nearest neighbor, you need 75 dimensions. So factor of 4 for linear method, but a factor of 30 for this nonlinear method. Okay, so the nonlinear method is really doing something here. And here again, it's just a little thing to show you for the words in the title of the paper, and there's more results in the paper if you want to see for other words. What were the 4 nearest neighbors before in this space? And what were the 4 nearest neighbors after? And the 4 nearest neighbors aren't completely preserved, but sometimes you get nearest neighbors that actually, you know, are totally reasonable, right? It's sort of interesting, like tractable, right? And the nearest neighbors before were wily or tractability, intractable, impulsion. And then you get tractability, which is 1. You get things like Rube Goldberg, things like ingenious. And some of these things reflect the context in which you might see this word, right? Model, you know, you get other things like modeling and models, which somehow get mapped closer than they were in the original space. Right? And for things like nonlinear, now you get things like, instead of diffusive, you get gravitational attraction or gravitation. So these things, even though they don't match exactly, they're sort of plausible. It shows that even the nonlinear embedding, even though it's doing quite a bit of reduction, it's not giving you nonsensical results. Okay, well, I think I've used up my time. So I will quickly conclude. Just how was this related to previous work? You know, the 1 second summary is that this model does optimize a similar objective function to UMAP and large-bit, but because we have a latent variable model, we don't need to rely on gradient descent and this negative sampling procedure. We have an EM algorithm and a coarse grading procedure. I'm actually hopeful that some of these ideas can be incorporated into these models, because there are some really nice large-scale implementations of these models, and I think these things could make them even faster. T-SNE, on the other hand, optimizes a really fundamentally different objective, which is very good for low-dimensional embeddings, but not so good in practice, it seems, for the embeddings that can't be used for visualization. What is next? And there's some really obvious directions for future work. First, there is just this line of work that's ongoing for making faster and faster solvers for Laplacian least squares updates. I used a generic off-the-shelf fast solver for these Laplacian least square systems, but I'm really hoping to get people who are interested from theoretical computer science. Maybe they can design a customized least square solver for the specific Laplacian systems that come up in my problem. You know, just how fast can we make those solvers? Can we somehow use this variance parameter to detect outliers? So I said before that outliers and the graph really play a key role in this embedding. All the machinery that you can just turn the crank on comes after you form the similarity graph. If there is a way to get rid of outliers, we might be able to come up with nice embeddings for much more noisier sorts of data sets. How high can we go with this coarse grading strategy? And the last thing is, one of the advantages of a latent variable model is that you can always throw in more latent variables. And so I'm kind of hopeful that for problems where there's more structure than just high dimensional inputs to map to low dimensional outputs, but maybe there's some additional structure in the high dimensional inputs that we want to preserve, or we have some more prior knowledge, maybe with additional latent variables, we can come up with even more customized models for this problem of nonlinear dimensionality reduction. So that is it. I'd be happy to answer questions now and stick around for as long as I guess it's early or mid-afternoon where you guys are. So if you're not already sort of lulled to sleep after eating lunch, just feel free to ask more questions.
Thank you so much, Lawrence. That was really fantastic. Let's open it up for questions. I definitely have a few, but I'd like to allow others to go first. We've been holding back. Jordan or anyone else? Do you have anything to say? Okay, well, let me kick it off with just some perspectives from a social scientist. So someone who trained in psychometrics and then, which is kind of associated obviously with factor analysis, exploratory factor analysis, confirmatory factor analysis, and structural equation modeling. And there's a whole kind of academic kind of knowledge culture surrounding a variety of different ways of evaluating the fit of models. And that involves, obviously taking log likelihoods, doing null hypothesis significance testing with chi-squares, and deriving various kinds of fit statistics for comparative model testing and evaluation. And so that seems like a really unique property of what you're doing here, is that if you could derive an overall log likelihood, then in theory, you're on the road to computing various fit statistics and comparing models with different numbers of latent variables, for example, more or less directly in very familiar ways. What do you think?
That's interesting.
You're hesitant.
You could compare these latent variables. I'll tell you why I'm hesitating. Because if you have a model like factor analysis, it gives you if you take sort of some data set and you fit it, and you hold aside you hold apart some other data points that were sort of sampled from the same distribution, right? You can use your factor analysis model to sort of see how well it fits the data points that you held out, and that gives you an idea of have you overfit, have you underfit, or things like that. And with these models, they don't really have that property, right? Because all they do is sort of non-parametric, right? For every input, they give you an output. But you can't take that model and then sort of compute an out-of-sample log likelihood. So I think that makes, it takes a little more thought. That's the way that I am most used to estimating how good a model is, which is like, okay, you've got some new data that you didn't use to fit it, and how well does it do on that? And for these models, that's a little problematic. But right. you are correct that if you were to supplement this by adding additional latent variables, or tying the inputs in some way, or tying the variances some way, or introducing some additional assumptions, you could directly compare those log likelihoods and maybe use that to determine which models are sort of quantitatively better, as opposed to just looking at the embeddings visually and saying which ones are right. qualitatively better. So.
Right, and that's exactly right, and that seems to be one of the main issues here, is that there's a question: what kind of criteria should we be using for model evaluation? So if you want to conceptualize it as a model at all, and that seems to be mostly aesthetic, and so getting away from that kind of aesthetic judgment and being able to do something like you're saying. I mean, even if you just penalize the likelihoods that you're getting based on the number of factors that or latent variables that you're estimating, then you're much closer to something that would be considered kind of familiar for a lot of people in the social and health sciences.
Yeah. I totally agree with that. I do think that for neighborhood preserving embeddings, there are some things that are sort of easy to compute. They're not probabilistic. I think the way that I and a lot of people think about these models is that the probabilistic framework is kind of a surrogate objective function for us. It's something that
Right.
we like because it's tractable and differentiable. In this case, it has additional structure. What we'd really like to do is give me an embedding in which, you know, all the points have the same nearest neighbors, right? And you know, there's no differentiable objective function for, you know, which points have the same nearest neighbors. So in some sense, there are these gold standards, you know, for any two different embeddings, you can just say what percentage of the nearest neighbors are preserved, right? That's not the thing that's directly being optimized, but if you could, that would be the thing you probably would like to optimize, right? So that would be another way of doing it, but it has the problem that it is not the thing you're directly optimizing. And if you are, for ideological reasons or philosophical reasons, sort of wedded to these probabilistic objective functions, then I think the road you're talking about makes a lot of sense to go down.
Right, right. And the philosophical or ideological approach in the social sciences is totally related to what you said earlier, which is whether or not you're treating this, or in the paper, rather, somewhere in the beginning, you're not necessarily treating this as some way of getting to the data generating process or the true model that describes what produced the data. You're doing something else.
Right, right. Okay, we got a question. Do you think such an approach can also be extended to a semi-supervised learning framework such as UMAP? Yeah, I think that extension is actually is fairly straightforward as it is in the UMAP case. In fact, this work in some ways grew out of work that I did 6 or 7 years earlier with a graduate student, where the goal was to construct a linear map that preserved nearest neighbors where you have class labels, right? And so in some ways that was a purely supervised approach for constructing a linear mapping where you can use these sorts of probabilistic objective functions. So I think if you combined that with maybe not fully labeled data, but partially labeled data, you could do that as well. Right. In some ways, the basic framework of this is very similar to UMAP. Where it differs is in the guts of the optimization. So most things that I think you can, most extensions of the UMAP, you can probably incorporate into this model as well. Good. Okay.
Let me ask, just, and some people might be thinking this as well, do you have a planning on producing a Python package or anything that kind of for people who are interested in, but
not MATLAB.
Plug and play. That's right.
I would. Here's the only issue with the Python package. The solver I used, I looked around for the best solver. You know, scaling this thing up depends on the best algorithm for these Laplacian solvers, right? That's sort of a, and I'm not going to implement a Laplacian solver. And you know, I kind of looked far and wide, and the state-of-the-art group, their code's in MATLAB. That's one of the reasons I did it in MATLAB. And you know, I could write everything else in Python, but somehow it's not going to be very satisfactory if for the core optimization I then have to hook it into MATLAB.
Right.
You go to that group's webpage and they say, you know, any day now we're going to have an implementation in different languages, which I assume would be Python because it's you know, but it hasn't come out yet. So I am every time I give this talk, I'm appealing to people in that community, point me to your best solvers in other languages so that this thing can be ported. Yeah, I do want to get that out. I think that's very important.
Great, thanks. Okay, anybody else? All right, you getting the clapping sign?
The clap for Python.
That's
all right.
Okay, great. Should we call it a day? What do you think? It's 9:30 for you.
It is getting late here.
Thank you so much. What I'll do is I'll stop recording unless anybody has any last minute burning. No? Okay.